This is Tsung Ye. I'm going to present our paper with title Dimensionality-Aware Redundant SIMT Instruction Elimination. GPU programming allows people to declare a multi-dimensional thread index. We scan across multiple benchmarks composed of 1D and 2D thread index. The layout of thread index in multi-dimensional thread blocks creates redundancy in the registers storing thread IDs. This redundancy propagates into dependent instructions. We show over 30% on the average SIMT instructions are redundant based on their operand values. To understand the source of the redundancy in GPU programs, we use matrix multiplication as an example. There are two matrices M1 and M2. Each matrix can be truncated into multiple tiling blocks. They are loaded in the shared memory with 2D thread index. However, we observe there are many repeated memory loads within a tiling block. It should be possible to remove these redundant memory load instructions in the matrix multiplication. GPU programmers can declare the number of the grid, thread block, and threads in the CPU code. One thread block can include multiple threads and warps. One warp has 32 threads in the CUDA programming. In this example, the host code creates one thread block with 16 threads. Thread X and Y index in the thread block layout represents the coordinates of vectors in one matrix. We can use this thread index to understand the source of the GPU program redundancy further. There is an example that is similar to the matrix multiplication. The x-dimensional thread index of one warp is 0 to 3 because the x-dimension size is 4. We have three instructions here. We move threadidx value to R1. The R2 is the R1 times 4. Then we loaded the data with the address based on R2 to R3. The R1 and R2 operand value in two warps are affine because they can be represented as base and stride. Therefore, we call the move and multiply instruction as an affine redundant instruction with affine output operand value. We also can observe the inter-warp R3 value shares the same pattern, but the intra-warp pattern cannot be recognized. We call low instruction as an unstructured redundant instruction. Our idea is to elect a single warp from a thread block to execute a redundant instruction and share the results with other warps in the thread block. We call the warp that executes the instruction the leader warp. Warps that skip the instruction and read the value are referred to as the follower warps. Let us look over how does DARSIE skip redundant instructions. There are 4 PCs. One thread block has 3 warps. GPU issues warp 0, PC 0 as T1. PC 0 is the redundant instruction because TX and R1 is a redundant register across our thread block. Warp 0 becomes the data warp of the PC0. DARSIE skips warp 1 and warp 2 PC0 as T2 and T3. PC1 is not redundant instruction because TY operand value. As T3, R1 on PC2 is overwritten. DARSIE can continue to skip PC2 with multiple versions of R1. DARSIE places additional barrier as branch instruction to ensure that all warp skipping instructions in the thread block executes on the same control flow path. Synchronization as branches is necessary to ensure that all warp skipping instruction in the thread block executes on the same control flow path. In addition, the synchronization also can help the reduction of the operand versions in code iterated many times. This additional synchronization will add overhead of skipping instructions. However, overlapping, non-redundant instructions, and frequent use of the thread block barriers within 2D benchmarks reduce the impact of the DARSIE additional synchronization. DARSIE also handles SIMT divergence. DARSIE elects the control flow path of the data warp as the majority path. Warps that diverge of the majority control flow path can no longer considered for skipping. Similarly, warps with intra-warp control flow divergence do not participate in instruction skipping. For instance, we continue to skip warp 0 PC3. PC4 is not a majority control flow path and is not considered for skipping. Previous work presents some solutions to remove redundant instructions. IRV hardware skipper recognize and skip reusable CPU instructions. UV leverages IRV to skip uniform instructions that comprise scalar operand values on GPUs. DAC compiler separates affine warps from non-affine ones and use affine address expansion engine to skip the execution of thread block affine instructions. Contrary to UV and DAC, DARSIE marks TB redundant instructions as compile time. DARSIE stops marks instructions to enter the pipeline. At that, DARSIE can remove three types: uniform, affine, unstructured, redundant instructions. DARSIE microarchitecture comprises instruction skippers and register version table. PC skip table records redundant instruction skipping status. Register version table keeps track of the data warp's redundant operands. Each cycle, a fetch scheduler in the front end of the pipeline fetch one of warps assigned it to the code. DARSIE skips instructions in the front of the pipeline before the iCache probe. To achieve this, we add hardware that acts in parallel with the fetch scheduler to skip some instructions while initiating a fetch for another. The instruction skippers relies on our compiler annotations to decide which instructions should be skipped. The PC skip table contains one entry for each PC currently being skipped. Each PC skip table entry places the PC of the leader warp and skipping status of the following warps. The PC skip table includes 5 fields to control the skipping logic. The warp waiting bit mask indicates which warps are waiting for this PC to skip it. Majority path bit mask indicates which warps are executing on the majority path. Its low points out the memory low instructions. Leader WB indicates the leader warp has written back the redundant instruction value. A PC correlator is used to minimize the skipping table read poll requirement. It correlates PCs based on exact matches. This helps limit the number of the assets mapped to the PC skip table each cycle. Let us see how the DARSIE updates the PC skip table during the instruction skipping. DARSIE skip warp 1 and warp 2 PC0 at fetch stage. And then DARSIE updates PC skip table. The warp 0 completes operand write back. PC skip table doesn't record PC1 because the PC1 is not redundant instruction. One PC skip table entry is removed when all warps with the same leader warp control flow path has been skipped. The register rename table maps warps register number pairs to this warps register number version number pair. When the kernel with the thread block redundancy is launched, we allocate a portion of the physical register file space for renaming. Each time a redundant register is written, we create a new version of the register tagged with the number of times it has been written by this thread block. As T4 warps through reaches PC0, skip the instruction, then executes PC1 using the old version 1 of R1. Warp 2 use R1v1 for its source operand because there has only been one write to R1 in warps 2 string. At T5, warp 1 skips PC2. Since all the warps in the thread block are done with R1b1, it can be released. Skipping low instruction presents a unique challenge, since memory dependency information is not embedded in the decoded instruction. Without complex and potentially expensive memory dependency tracking hardware, we cannot guarantee that a stored instruction does not update memory as the location a skipping low instruction reads. To simplify the decision, the DARSIE avoids the memory dependency problem by removing lower PCs from the skipping table when one of the two events happens. The first event is when the store instructions in this TV occurs. The second event is when the global communication primitive are executed. DARSIE was implemented in GPU SIM version 4.0. We use GPU watch to measure the energy consumption. DARSIE works on a media Pascal architecture with 28 SMs. DARSIE reduced 24% executed instructions in 2D benchmarks. DARSIE outperforms UV and DAC because DARSIE can remove 3 types: uniform, affine, and unstructured redundant instructions. DARSIE improves 30% performance over the baseline in 2D benchmarks because it's high skipping bandwidth and is able to skip 3 different types of redundant instructions. UV is typically limited by fast throughput since it can only remove uniform redundancy as the issue stage. DAC only skips uniform and affine instructions. DARSIE reduced 23 energy consumption on the average because DARSIE removes different types of redundant instructions. In conclusion, DARSIE makes use of compiler and hardware instruction skipping logic to remove GPU SIMT redundant instructions. DARSIE marks redundant instructions as the compile time. DARSIE leverages PC skip table and register version table to realize instruction skipping and operand value sharing. DARSIE can improve 30% performance and 23 energy on 2D applications. Thank you.